Sorry, just say that again.
One that maximizes steady state consumption.
That's right. This word steady state is the important one. You're right. So the golden rule of saving. So notice that you have some n plus delta, you have some k, you have then some f of k. I'm just drawing. So these are all, you have all these in the vertical axis, horizontal axis, you have k. So basically you're saying that whenever you have a steady state value of capital labor ratio, you have a corresponding C star also associated with it, right? Let me say K1 star, let me say this. Now, but if you were to change, let this be S1. So if you were to change the saving rate, then you would get another corresponding level of K2 star. So suppose saving rate were to change from S1 to S2, something say like this, let it be higher. Then you will get some K2 star and correspondingly you will get C2 star also, right? Now, the golden rule of saving says that you want to find out that saving rate which is going to give you the maximum value of consumption. And that is what is called as the golden rule of saving. So the idea here is then that, so this was graphically, mathematically speaking, you would have a C star which would depend upon S, as we just saw, and this expression that you will have, which is nothing but 1 minus S times F K star. This is what you have, and K star is in turn a function of S. So this K star, let me write it like this then. What I'm trying to say is F A star S. This is the way I'm writing. So mathematically, how would you derive this? You will differentiate this C star with respect to S, and you will try to find the maxima, the point of maxima of this function. So the first order condition would say that this should be equal to 0, and the second order, you will ensure whether you're looking for a maxima or not. So del square C star S del S. So what should be the sign here for a maxima to be obtained, right? So you'll basically differentiate this C star equation with respect to S, and you can also follow the chain rule here. So you can basically say that this would be the same as del C star S upon del K star, and then del K star S by del S. So you can do it this way. So I'll just give you 2 minutes and then you tell me the expression that you will get. Can you all just solve for yourself? I'm waiting for you. All right. We get this expression that you see on the screen as a final one. So when you differentiate this, you will end up with this. Notice that this term will be 0 when the term inside the square bracket will be 0, because del k star by del s is not 0. The only way this can be 0 is that this term is set equal to 0. So you will have f prime k is equal to n plus delta. So that's the condition you end up with. So golden rule of capital labor ratio is such that it satisfies this equation. Now you have the functional form of the production function that's given to you. You can plug that back here and you will be able to obtain the exact value of the golden rule of capital labor ratio when you have the Cobb-Douglas production function. So if you plug in those values, what you will end up with is A alpha upon. So you can check for yourself that you will get this. Plug back the first derivative of Cobb-Douglas here, production function here, and you'll be able to obtain this. So the idea here is that, so what does the golden rule of capital labor ratio ensure? It ensures maximized consumption in the steady state. So the concept of dynamic efficiency is linked to this only. So now whenever you have, so if you compare now K star that you got earlier with Kg, so let's write, so K star that we had got, I had said that this was SA upon N plus delta 1 upon 1 minus alpha, and Kg, what you're getting is now, do you think that this, okay, before I ask this question, what do you mean by dynamic efficiency?
Ma'am, basically at higher levels of capital stock, we are not able to achieve the maximized consumption. So we need to decrease the capital stock to the steady state capital stock in order to achieve the highest level of consumption. That will be at the golden rule.
Okay. Yeah. So dynamic efficiency basically says that if you can increase your utility, which is coming because of consumption, without making yourself worse off, then you are sitting in a position of dynamic inefficiency. So I'll repeat once again. If you can make yourself better off in terms of increasing your consumption, which gives you a higher utility, if the consumer can be better off without sacrificing utility, without making any other sacrifice, then it is a case of dynamic inefficiency. Dynamic efficiency is that if you have to achieve something, a higher level of consumption, but for that you make a sacrifice, then that is a case of dynamic efficiency. So what we see is that in case your steady state, this is SFK, this is K star, and suppose this is, now you know, golden rule of capital labor ratio can be either to the left of K star or to the right of K star. So let's say golden rule of capital labor ratio is here. So if you are to the right of the golden rule of capital labor ratio, what this just means is, as correctly pointed out by one of your friends, that if you over accumulate capital stock beyond this golden rule of capital labor ratio, then you are basically accumulating capital by sacrificing consumption, and you are not at the highest level of your consumption. So you can increase your consumption by moving from K star to Kg star, and all you have to do is do less accumulation of capital and consume more. So less accumulation of capital does not involve any sacrifice on your part. So that's why you can achieve higher level of consumption without making any sacrifice. But suppose, so all the points to the right of Kg star, These are all points of dynamic inefficiency. When you overaccumulate capital beyond kg star, those are points of dynamic inefficiency. Now, what happens if you are to the left of kg star? What happens is that when you are to the left of kg star, let me just denote it the other way now. Suppose kg star is here and your k star turns out to be here. So suppose your saving rate is such that it is leading you to a steady state k star such that it is to the left of kg star, then it's a point of dynamic efficiency, because to be able to achieve higher level of capital stock, which is kg star, you have to sacrifice your consumption. All right. So that is why here you have to make a sacrifice in order to achieve a higher level of consumption levels for the future. So C star G is in the steady state. So this is the consumption in the steady state corresponding to a kg star. So which means that you will be able to achieve the CG star period after period. In the steady state, the level of consumption labor ratio would not change. So you will be able to achieve C star G period after period by making sacrifices today, which is basically increasing your savings rate, in the current period. And so, which will mean a sacrifice of consumption in the current time period to be able to achieve higher level of consumptions in the steady state in the future. So that's why this involves a sacrifice, and therefore it's a point of dynamic efficiency. And because of this, we can draw this C star curve, which we differentiated also. Let me just go back and draw it there only. You will be, yeah, this curve, we can draw it as like this. So, so this is C, S, and this is S. And so there is some S golden rule, which will, some saving rate, which will ensure the highest level of consumption. And that is what is called the golden rule of saving. All right. So we have derived the golden rule of saving, but the steady state that we got in this model, is it dynamically efficient? Let me go back to the whiteboard. Yeah. We are saying the question now is this K star a dynamically efficient outcome? What do you think?
Will it not depend on the value of S?
Yes. Vis-a-vis? Value of S vis-a-vis?
Alpha.
A. Oh, yeah.
Alpha.
That's right. So here you just have to check what will be the value of S vis-a-vis alpha. And you're absolutely right. If S is greater than, let me write it on the next page. Yeah, okay, let me write here only. So if S is greater than or equal to alpha, then K star is
dynamically inefficient.
Yes, dynamically
Inefficient.
Yes, inefficient. And if it is S is less than alpha, then it is dynamically efficient. So if S is less than alpha, then you have dynamic efficiency. All right. So,
ma'am,
sorry, it's the other way around. Sorry. It's got to be greater than strict here, and this has to be less than or equal to. Yes, correct. So even if you are at kg star, you have achieved the maximum level, and you are at a position of dynamic efficiency. So it will be, so the weak inequality will be here, S less than or equal to alpha. It will be a case of dynamic efficiency. Yeah. Any doubt someone wanted to ask? Okay, so this is about efficiency, dynamic efficiency. Now the question is, if an economy starts with initial capital labor ratio K0, derive the expression of the transitional time path from initial condition to state condition. So you have seen where you begin with and where you end up with. So the end ultimately you end up with the steady state, and you begin with some capital labor ratio K0. But what happens in the interim? So when in the state transition equation, you set K dot is equal to 0, you are able to achieve a level of capital labor ratio which is not changing over time, which is the steady state value. But how do you reach the steady state value? That's the question. So for that, you don't have to set K dot equal to 0 in the state transition equation. And you see how this K dot will behave when capital labor ratio is in a certain region, either below K star or above K star. So let's see the time path now. So what we have to do is, we don't have to set K dot is equal to 0. We get a state transition equation, which is SFK minus. This is what we have, right? So now you just have to make a few manipulations here. So mathematical manipulations. So note that you can define growth rate of capital stock. Sometimes it is also denoted by gamma K or GK, whichever. So this is basically the growth rate of capital stock, which is defined as K dot by K. Basically, this is telling you how capital will grow over time, because you have K dot by K here. So you can write this as SFK by K minus N plus delta. So this is how you can write it, right? Now, again, just doing a few manipulations, you want to convert this now into a differential equation. As you can very clearly see that you have a differential equation working here. So first, let's substitute for Fk. Let's say that this is SA K to the power alpha upon K minus N plus delta. So I've substituted for the Cobb-Douglas production function. And now what you just need to do is, you need to work out a differential equation here. So you'll just make a few manipulations. So you'll have K dot by K raised to the power. Now I'm trying to bring this down over here. So this is K raised to the power alpha is equal to So what I've done here is, I can write this as alpha minus 1. And if I divide throughout by K to the power alpha minus 1, K to the power alpha minus 1, K to the power alpha minus 1, this is what I will end up with. So here I'll have K to the power alpha minus 1 plus 1 in the denominator, which will give me K to the power alpha. I take this on the left hand side and I get a plus, and then K to the power 1 minus alpha if I put it in the numerator, and so on. So this is what I end up with. Now notice that again, here the powers of K are not 1. This is a polynomial differential equation in K. Now, how do we make it? How do we simplify this? So what we do is, we define a new variable V, which we define as K to the power 1 minus alpha. And what we work out for is V dot, which is dV by dt. And if we want to work that out, if it is equal to K to the power, if V is equal to K to the power 1 minus alpha, then this will work out to be 1 minus alpha K to the power minus alpha dk by dt. This is what we will end up with. So which means that V dot is equal to 1 minus alpha k to the power minus alpha k dot. This is how these are related. So note now, in our original equation, in this equation, this one, we'll plug in the values now in terms of v. Now we know we have defined a new variable v in terms of k, and so we will replace v instead of k everywhere in this equation. Let's see what happens. So if we do that, we have v dot upon 1 minus alpha k to the power minus alpha. So instead of k dot, I've written this, and you have k to the power alpha here. Now plus n plus delta k to the power 1 minus alpha. Now, if you have to, if you just multiply, yeah, so if k to the power, just a second, k to the power 1 minus alpha is nothing but v, and then minus SA. You can then write this as v dot plus 1 minus alpha n plus delta v minus s 1 minus alpha a is equal to 0. Everybody convinced? This is just mathematical. Yeah.
Ma'am, can we take the value of k dot by k alpha and just put it straight into the...
Yeah, that is also possible. So whichever way, we just want to substitute, instead of k's, we want v's. This just gives us a first order differential equation in terms of v now. Rest are all parameters, as you can clearly see. S, alpha, a, these are all parameters. So now you just have a first order differential equation in terms of v, and the solution to that equation, going back from mathematical textbook, the solution to this equation is given as, so Vt is then defined as C. This is some constant, arbitrary constant, e to the power minus, okay, let me first write the general expression. So if you have any first order differential equation, which you can write as x dot plus ax is equal to b, then the solution to that equation, you can refer to any mathematical textbook. This is c e to the power minus at plus b by a. This is the solution. So now we have first order differential equation in terms of v. Now our coefficient here, as you can clearly see, so if you write this equation in terms of this, then your a is this coefficient, and if you just take this on the other side, b is this coefficient, right? Now if you just use this solution to the first order differential equation and write the solution now in terms of v, so this was the general thing, so vt will be written as c e to the power minus 1 minus alpha n plus delta t plus sa 1 minus alpha. This is b by a, right? So this is b and this is a. This will cancel away and you will end up with this. This is the solution. Now, this is the general solution. The only unknown thing that you know is, unknown thing here is this constant c. Now, you will be able to discover this constant c if one of the boundary conditions is given to you, and let us say the initial value of v naught is given. Why do I say that? Because in the question, initial value of k naught was given to us, right? And as we just defined, v is equal to k to the power 1 minus alpha. So if k naught is given, then v naught is also given to us in some sense, indirectly. So if I evaluate this v at time period 0, because I know capital stock at time period 0, that is given in the question, I can write this as, now instead of t, you evaluate it at t is equal to 0, the solution at t equal to 0. So you will get c plus SA upon n plus delta. So from this, this implies C is equal to V naught minus SA upon n plus delta. V naught is given. It's not unknown, it is given because K naught is also given to you, right? So, so basically you can also say that this is K naught raised to the power 1 minus alpha. C is equal to minus SA upon N plus delta. Now in this, everything is known. So this is, and now you can plug back this value over here in the solution. So you will get the specific time path of V as a solution to the differential equation that you have. Now let's just do this. So first you'll plug back the value in terms of C here, the C value here, and then you will write this V back in terms of K now, because now we are interested in the solution of K instead of V. V was just a variable that we were using for our convenience, but ultimately we want the solution in terms of K. We want the time path of capital stop. So substitute for C, substitute for V, and rest are all constants here. So you will then, if you do all that, you will end up with the following. So you will end up with KT is equal to SA upon N plus delta. Just a second. Yeah, you will substitute that back here and you will end up with this. You'll just take a few things common and put other things together. So simple manipulations, you'll end up with this. All right. Now you very well know that this was nothing but K star. This entire thing was K star. So you can write this as KT is equal to K star plus K naught minus K star this is what you write. Looks like. So this is basically how the capital stop will evolve if you were to start off at a point which is not at the steady state. So if K naught is less than K star, so if even in Barrow Salai Martin, let me just share with you once again the textbook. They have defined exponential growth rates. Let's go back here. Yeah, this one. So when you write LT as e to the power NT, you're basically saying N is the growth rate of labor force, right? So similarly, if you look at this exponential term here, this is basically telling you how this coefficient here, this is basically telling you how what is the growth rate of capital stock if you were away from the steady state. So if K naught is equal to K star, then of course there is no movement of capital. Then this part is 0. But if K naught is not the same as K star, then of course you will have capital growing at this rate, and the distance will also matter. It will be multiplied with this distance away from the steady state, this gap. Now, how do you mathematically define what would happen if you were not at the steady state? Well, you will see that if you work out dk by dt from this equation, it turns out you will end up with K naught minus K star e to the power minus 1 minus alpha N plus delta t, and you will multiply this entire expression with minus 1 minus alpha n plus delta, right? Agreed. Now, is this positive or is this negative? This dk by dt, is this expression positive or negative? So if k naught is less than k star,
on the
yeah.
now it depends upon whether we are away like in the left direction of the steady state or towards the right direction.
Yeah, that's right. Absolutely right. So if you are, so as I said, if you are to the left of k star, if k naught is less than k star, then this part is negative. And this part, these are all positive values, right? And you have a negative term here. So overall, when you have k naught less than k star, you have dk by dt, which is positive, right? So which means that if you start off at a point, at an initial value of capital stock, which is below the steady state, then capital stock will grow over time. Capital stock will increase over time because this expression is positive, right? And vice versa, of course. If you start off at a point to the right of k star, then this term in the bracket will be positive, but you have a negative term here. So dk by dt will be negative when k naught is greater than k star. Everybody agrees? Any problem here? Okay. So basically we are trying to say that if you were not at the steady state, why did we do all this? We were trying to see the transition dynamics, which means that if not at the steady state, if you were to begin somewhere else away from the steady state, then how will your capital labor ratio move? In what direction will it move? So mathematically, we are establishing that if you are to the left of k star, then you're going to converge towards k star because k is going to increase, and vice versa. If you begin to the right of k star, then your capital stock will decline over time, and you will converge to the steady state ultimately. So that's what you get here. Now, if I were to represent this graphically, what I'm trying to say here is that let me denote this as k star. If I say that if I start off at a point which is now how do I denote this? I'm denoting this as time. So if I start off above k star, which means I am to the right of k star, then capital stock will fall, right? Yeah, but I don't know. So it's going to here, it's going to go down. You have capital stock KT on the vertical axis. So capital stock is going to go down, but I don't know whether it will go down in a straight fashion this way or this way. I don't know, but it's going to decline. That's what I know for sure. Similarly, if I start off below k star, then it's going to rise, whether this way, or this way, we'll just see. How can you work out the curvature? If you just take the second derivative, you will just see that this turns out to be, I think it turns out to be positive. Yeah, let me just check. Yeah, so you can do the second derivative and it will turn out to be positive. So which means that this is the curvature and this is the curvature. So you'll have this sort of a movement.
And the value of second derivative will be positive and negative. So in the above one, it's a positive, and in the below one, it's a negative.
Yeah, that's right. So so which means, yeah. So if k naught is greater than k star, then it's going to be positive unambiguously, which means that this function is declining at an increasing rate. Just a second. Am I saying this correct? So what I'm trying to say here is that if k naught is less than k star, two things will happen. First is that dk t by dt will be negative, and also dk t by dt square will be negative. let me write the expression. Let us just work this out, what it's working out to be. So I'm getting b square k t this is what we'll end up with. So now if k naught is less than k star, so this part will be negative and this is obviously positive. So yes, we'll have dk that dkt is negative. That's right. So it's declining at a decreasing rate. Here. So the slope becomes flatter and flatter. It is decreasing at a decreasing rate.
Ma'am, but mathematically it is declining at an increasing rate. Like what math suggests. Because it's a convex state.
No, when it declines at an increasing rate, then the curvature is like this.
Yes, ma'am.
No, ma'am.
Yeah, because this is declining, but the slope is becoming steeper. So the rate of decline is increasing when you have a concave sort of a curvature. So this is decreasing at increasing rate.
Okay.
So I think this should turn out to be positive then. Yeah, this should be positive.
Ma'am, when k naught is less than k star, shouldn't dkt by dt be greater than 0?
Oh, yes. I think, let me just repeat this part. Yeah, sorry. I think I've messed up the signs. Yeah, so let me just reconcile all this. Just a second. So let me just write this sign. This will be positive, and if this is the case, then this will be negative. Yeah. Yeah, that's right. So we are considering this is the case. So let me write this as case 1. So this is case 1, and this is case 2. So when we start off at a capital initial level of capital labor ratio, which is lower than K star, then your capital stock is rising at a decreasing rate. So that's what these signs will mean. So when you have this positive and this one second derivative as negative, then it means that this one is saying that it is increasing, but at a decreasing rate. So the slope is slowly becoming flatter. That's why the rate is decreasing. And vice versa in case 2, when you will have k naught which is greater than k star, then dk by dt will be negative and d square k by dt square will be positive. So it's decreasing at an increasing rate. Just a sec. Let me write it again. So case 2 will be k naught is greater than k star. And so your dk t by dt will be negative. Yes, will be negative. And d square k t by dt square, this would be, this is greater. So this would be positive. Yeah. So then what we are saying is that if you start off at a value above k star, which is this case 2, then in that case, first of all, we know that it's declining over time. Capital stock is declining over time. And it is declining at a decreasing rate.
But ma'am, double derivative is positive.
Yeah, double derivative.
So how it will decreasing at increase? It should be decreasing at increasing rate.
मैम आई थिंक ये ना मैथमेटिकली कंसेप्ट है कि इसमें ना नेगेटिव में अगर डिक्रीज होता है लाइक -10 से -9 होता है तो पॉजिटिव कंसिडर जाता है, तो मतलब इकोनॉमी वाइज मतलब इकोनॉमिक वाइज थोड़ा अलग कंसिडर जाता है, एक्चुअली सोचा जाता है।
Yeah, because he's right that in mathematically, when you will have declining values, basically, so basically if you go from -6 to -9, so what's happening here? So you
decreasing.
Yeah. So in absolute terms, the value is increasing, but you're basically decreasing. It is happening at a same concept applies here also. If you have, so what I remember from my mathematical results is if I can have three kinds of curvatures. I can have this, I can have this, and I can have this, and I can have this. I can have rising this way. Yeah. So these are rise and these are falls. You know, so dk by dt, basically this is negative here. When we say it's falling, then we're saying that dk by dt is negative for sure in both the cases. But because this is concave from below, so your second derivative d square k by dt square is going to be negative here. And for this one, dk by dt is negative, and d square k by dt square, it's going to be positive because it is convex from below. So therefore, this is going to be positive. And similarly here, dk by dt is positive, and d square k by dt square, this is going to be, this is concave from below, so this is going to be positive. This is, so mathematically, if you get these two values, then this is your curvature. If you get these kind of values, then this is your curvature. I mean, this is what I remember from my mathematical textbooks. Now, so here we say that this is basically rising at increasing rate. And here we say rising at decreasing rate. Falling at increasing rate. And this is falling at decreasing rate. Now, the same signs on second derivatives, but for rising and falling, when we say increasing or decreasing, these are different connotations that we attach.
No, I think this will only be the case if we consider the double derivative in modes. Otherwise, it's going to be the case.
You can check from the textbooks. This is what I clearly remember, and I doubt I will be wrong here. So just check back from your mathematical textbooks, and but I very surely remember that this is the case, and these are the interpretations. If I'm wrong, just let me know. Just write to me. Yeah. So so similarly here also, the kind of graph that we'll get from observing these values when your k naught is greater than k star is this. So when k by dk by dt is negative, it's basically capital stop is falling over time. And when the second derivative is positive, it is falling at a decreasing rate. That's what we observe. Right? And so the graph then finally looks like this. So capital stock is moving in a way such that it will at some point asymptotically reach the steady state. It will converge to the steady state. Okay. So basically this was the transitional time path from the initial condition to the steady state condition. The solution KT that you got from the difference by solving the differential equations, that's the expression for the transitional time path. Okay, derive the factor incomes in the Solow-Swan model. Very simple. It's also given in the textbook, and you've done it, I think, umpteen number of times at the graduate as well as the postgraduate level. Yeah, these equations. These are simple, straightforward equations here, right? So, so here on the left-hand side, you have marginal product of capital, and here you have marginal product of labor. And this is equal to W, and this is equal to the rental rates of capital. And you define small r as basically F prime K minus delta. So this is basically marginal product of capital minus the depreciation rate. That's how you define the small r. Derivation you can do for yourself. I mean, it's very easy. Comment on the dynamics of the factor incomes during the transition towards the steady state. So now we just so these are, if you're at the steady state, then you can write this as F prime K star is equal to marginal product of capital. So, and you can write this as you can replace the values of K star here basically at the steady state level. But what if you were to make a transition towards the steady state? So suppose you are not, so this is equal to W star if these are replaced by K stars here. And this is equal to R star. And the small R star will be F prime K star minus delta. So these are your interest rates and wage rates in the steady state. But what if you were not in the steady state? How would your wage rates and rental rates behave? So what would happen? So suppose you were to start off at a point which is to the left of the steady state. So suppose you start off at a point which is K less than K star. Now, if you were to move towards the steady state, so we just saw that the transition dynamics of capital labor ratio show that if you are at a point, if you have a capital labor ratio which is less than K star, then K will rise, right? And we will ultimately reach the steady state. So if you start off at a point K less than K star, K will rise. And what happens when K will rise? When K rises, the question is what happens to W and what happens to the rental rates? So what do you...
Marginal product of capital will rise, so the rental income I can say rise.
My marginal product of capital will fall.
Sorry, fall.
Yeah. So marginal product of capital will fall and rental rates will fall. So because this is the relationship in general also, R is equal to F prime K minus delta. If marginal product is falling, the rental rates will also fall. So K by L, this is what is K. So whenever K rises, it means that basically this is rising. This ratio is rising. Now this K can rise because of two reasons. Either the capital stock level is rising or the labor stock is falling, right? So in other words, it also means that when K is rising, and two possibilities are that labor stock can fall or capital stock level can rise. So it also means that marginal product of labor is rising. In other words, when we say K rises and marginal product of capital falls, similarly, the connotation can be that marginal product of labor rises, because rise in small k can be because of a fall in L, capital L. And so marginal product of labor is rising. So when the marginal product of labor is rising, then what do you expect to happen to wage rates?
They will rise.
Yeah, you expect wage rates to rise. And you can check this also mathematically. For rental rates, it's very straightforward, you know, that if a marginal product of capital rises, your rental rate, marginal product of capital rises, rental rate rises. And if it falls, then rental rate will also fall. It is very straightforward to see. But from this equation, it's not very straightforward. So you can just check for yourself. You can differentiate. Let me just write it on the whiteboard. Yeah. So you have this W equation, which is F K minus K times F prime K. So you can work this out as follows. So you'll have del W by del K and see what sign it has. So you can just differentiate and see for yourself. Are you getting this to be positive? That's the question.
Yes, ma'am. Yes, ma'am. We are getting positive.
Yeah. So yes, you should get it as positive. So you will get this as minus K F double prime K. This is what you will get. F double prime K, because you have a neoclassical production function, there are diminishing marginal returns to K. And so therefore F double prime K by definition is negative. So because this is negative and you have a negative here, therefore this is positive. So which is corroborated by theory as well, that when capital labor ratio rises, marginal productivity of labor rises, and as a result, the nominal wages that are offered to the laborers, those are also rise. It becomes profitable for the producers to employ more labor because the marginal productivity of labor is higher, and in order to employ more labor, they offer higher wages. So that's the line of reasoning. Okay. So this was about, you know, transitions towards the steady state, and we were still working in the Solow model framework. Now we change our approach a little, and what we saw in the Solow model was that we were using a production function that was exhibiting demands at all points of capital labor ratios. But what if this assumption is not satisfied at all points? So basically, we have the poverty trap model, which basically says that you can have diminishing marginal returns, but sometimes in the interval, you may have increasing returns, or there is also a possibility of constant returns. So poverty trap model, I've just discussed this with you. It is basically derived, the basic crucial assumption that is giving rise to the poverty trap is existence of increasing returns to scale in the interim. There is some portion of capital labor ratio where you do get increasing returns to scale. And that is a crucial assumption that gives rise to the poverty trap. Let me open the textbook. Yeah, we can read about this. Page was it? Yeah. So so the assumptions now change a little. Let's see what the assumptions are. Well, it says that, yeah, it says that, so how they define poverty trap? It's a stable, steady state with low levels of per capita output and capital stock. And the outcome is a trap because if agents attempt to break out of it, the economy has a tendency to return to the low level stable steady state. So basically, we are saying that if you have multiple steady states, one is at low level of capital stock. Let me say you have K1 star, K2 star, and then K3 star, suppose. And these are all steady states. And suppose this one turns out to be stable, this one turns out to be stable, and this is unstable. So basically, even if you are in this region, you tend to move towards the stable steady state, which is at a lower level. And so any country which is in this region between K1 star and K2 star, if it wants to travel to K3 star, it is a big problem, because till you hit K2 star, till you go beyond K2 star, you will not be able to reach K3 star. You will be stuck at K1 star, because the system, the dynamics system is taking you back towards K1 star if you start somewhere in the middle of K1 star and K2 star. That is what we are calling a trap. But how do we get these multiple steady states, and why the middle one is unstable and why the lower one and the higher one is stable? That is because we have changed a few assumptions in the model. And let's see what those assumptions are. So here we say that in the neoclassical production function, we observe the average product of capital declines with K. And how diagrammatically you can just see. So if you have a concave production function, a neoclassical production function, where initial value is infinity, and of course at some point the slope becomes, let us say, Fk. This is K. So Fk by K basically is basically your, if you imagine the slope of this ray from origin to the point, this is what gives you the slope here is Fk by K. And this is also the average product of capital. This is also Y by K. This is the average product of capital. So if you have a neoclassical model and you have diminishing marginal returns, then you will always get a capital stock. You will always have average product of capital, which is going to decline. But this average product, this is a crucial assumption, may rise with K in some models that feature increasing returns. So this is the crucial assumption that is giving rise to the trap. So let's see. So one way for the poverty trap to arise is for the economy to have an interval of diminishing marginal average product followed by a range of rising average product. That's how you get this. So this is the crucial part, which is giving rise to the poverty trap. Okay, let's just see. So the setup of the model is as follows. How can we get such a situation? We are saying that let us imagine that there be two kinds of production function. This is the old production function where the technology is old, and the country also can achieve high productivity technology and achieve new modern technology, which is denoted by B. So there are two kinds of production function. One which is produced where the production is happening using traditional methods, and where the other one where the production is happening using the modern methods. And of course, we know that B is greater than A. The productivity of the modern technology is higher than the traditional one. Now, what we are also assuming is that the country as a whole is assumed to have to pay a setup cost at every moment of time to cover the necessary public infrastructure or legal system, whatever. So we are saying that there is some cost involved in setting up this modern technology. And we are saying that this cost is proportional to the labor force. So we are saying that every unit of labor must pay B units as cost to set up this technology. So the total cost to the government will be times A. All right. Now, this of course is borne by the government and financed by the tax rate at B on each worker, and so on and so forth. Now, if you write it in terms of per capita, so what you get is that the production function net of cost is this. So there is some fixed cost involved in this technology, and so that's B times L. And if you write it in per capita terms, then this is the production function. This is what it looks like. Now, when will the government decide to buy modern technology? When will so first thing is that if the government does buy modern technology, then everybody is going to use it. Nobody will use old technology. Why? Because if the modern technology is available, it is inefficient not to use that technology. Why should we not produce more when we have already bought the technology? So if the government decides to buy it, then everybody uses this technology, modern technology. And if the government doesn't buy, then of course the default is to work with old technology. But the question is, when will the government buy this technology? When will the government install this technology? So the idea here is that if b k to the power alpha minus b is greater than a k to the power alpha at the same level of k, then the government decides to invest in the new technology. And if you solve this equation, you will end up with this. You will end up with k greater than b upon b minus a 1 upon alpha, right? So this is what you're calling as k bar or k tilde, whatever this is, this one, k bar, k tilde. I think in the notes it's k bar, here it's k tilde, but whatever it is, this term you're calling as k tilde. And so you're saying that if the capital labor ratio in the economy is greater than this k tilde, then the government will decide to and buy the new technology. So you're saying if it's greater than or equal to k tilde, fine. So when it's equal, the government will be indifferent basically between the new and the old technology. So it doesn't matter. But if k is less than k tilde, then the government will surely not buy this technology. So what affects this value of k tilde? So the higher the value of k tilde, and the more it will be difficult to achieve that k tilde, and so the less possible it is for the government to buy new technology. So basically the question is, what is deciding this value of k tilde? The higher the threshold level, the lower will be the possibility that the government will buy this new technology. So the threshold level basically is dependent upon this b, small b, and the differential b minus a. Alpha is the again a constant. Yeah. So the crucial fact here is that if b minus a, this capital B minus a is high, which means that the modern technology is far more productive compared to the old technology, then this k tilde will be low. And as a result, the possibility of the government investing into modern technology would be greater. Secondly, if the cost of installing this new technology, small b, is lower, then also the chances are that the government will be able to invest in new technology compared to the old. So these are the two conditions under which threshold level will be lower, and the investment by the government in new technology, the chances would be higher. Any problem till this point? Any clarification you want?
Ma'am, please can you repeat the b minus a case, like when it's high?
Okay, so I'm saying that k tilde is affected by, is high or is low, I could say, if b is low, that's one, and or, so that's for first case, and second case is when b minus a is high, right? So when I say b minus a is high, what I'm saying is that the technology b and technology a, the difference between the technologies is high, which means that the modern technology is far more productive compared to the old technology which is in place. That is when the government, when the new technology is actually a great improvement over the old technology. That's when the government will decide to buy new technology. There are incentives for government to invest in the new technology. And when small b is low, the per unit setup cost is low. That's also when the government is incentivized to invest in new technology compared to the old.
Yes, ma'am, got it. Thank you.
All right. So if this is clear, then let me just clear out all this. Now let's plot the production functions. How will these production functions look like? So when you plot the production functions together on the same graph, both with the old and the new technology. So this is your production function with old technology, and this is the production function with new technology. And there is some overlap. And of course, as you can see that this is some fixed cost here, which is, so if K is 0, let me just move up. So if K is 0, then this new technology involves some cost here, which is negative. So that's why it will have a negative intercept here. Okay, so now can you see something very clearly? So the effective part of this will be the bold line that you see here. The effective production function is the bold line that you see here. But notice what's happening. If I draw the rays from origin to the points on the production function, so basically I want to look at the average product of capital, which is Fk upon K. If I want to look at that, notice that average product of capital, the slope of this line versus this line. So the slope is falling till you reach this point. And then again, it starts rising. Note in this point till you reach this point, suppose. And then after this, if it's a straight line, then it remains the same. And if it is diminishing returns, then it again starts falling. So are you getting my point? Till this point, average product of capital is falling. And then it starts rising in this region. And then after that, depending upon whether this is a straight line, it is constant. Then if it's a straight line, then average product of capital is constant. And if it is diminishing, then your average product of capital again falls. There can be two possible cases beyond this point B. Is everybody okay with this? Any doubts? So what this assumption has done is, when we introduced two technologies and we were saying that because of diminishing marginal returns, we were not getting that sort of multiple steady states. And here in this case, if there is a range where average product of capital is rising, then we will be able to end up with multiple steady states and the situation of a trap will arise. So let's see how this will give rise to a trap. So if you were to plot this average product of capital, now you have to go back to the Solow model. If you remember how we were to plot these steady states, we were plotting them as like this. Let me just show this to you. Let me draw them here side by side. So first let me explain this diagram. So this diagram is saying in this range, average product of capital is, so let me say Fk by K is falling. In this range, Fk by K, it's rising. And again, there can be two possibilities. Either it's constant or it's falling. Fk by K is falling. So notice that, how did we get this diagram? Now that's the second question. We were plotting, this is n plus delta line, right? And this is Sfk by K. So we were saying Sfk minus n plus delta K is equal to K dot. That's what we were saying. And then we said that in the steady state, if you want the steady state, then K dot should be 0. So if K dot is 0, then we can write this as Sfk by K is equal to n plus delta, right? So Sfk by K is equal to n plus delta. So we have basically plotted Sfk by K and we have plotted n plus delta, and we have found the points where the two are the same. These are steady states. These are points of steady state. So this is one steady state, this is another steady state, and this is the third steady state.
And how did we get this curve for SFK from the production function?
Yeah. So I just told you, let me clear this and go back up. Notice, yeah. So as I said, any ray from origin to a point on the production function, the slope of that ray gives you the average product of capital, Fk by K. Right? So I'm saying, yeah, so we have just qualitatively plotted that we had just discussed here. So we've just qualitatively plotted the, so if you just multiply this with S, it doesn't make a difference because the curvature is ultimately decided by this. It's just a constant term that you're multiplying with. The curvature is decided by this, whether it's rising or falling. So just a second. Yeah, scroll down back. Yeah. So let me just say a few words here. So basically, this interval, for this interval, this interval, average product of capital is rising. So S times the average product of capital will also rise. And that is what we have plotted below. That for some interval, it's going to rise and not fall throughout. This one. So if you want to draw the corresponding points, so this is what gives you K bar, K tilde that we were deriving. This is where K tilde will lie. And this is also, let me go back up. Yeah. So let me say this is, let this be point O, let this be point P, let this be Q, basically. So I'm saying that now correspondingly, this point P and Q and O will plot corresponding points in the other diagram also. So between P and Q, average product is falling. This is P, and this is Q. Between P and Q, sorry, average product is rising, not falling, rising. And between O and P, average product is falling. And beyond Q, there can be two possible cases. Either it can be the same or it can fall. Right? So we'll just plot O, P, and Q in the other diagram also. Yeah. So you'll have O here, somewhere here. Then you'll have P here, Q here. And then there are two possible cases beyond Q. Right. Now, so our objective was to look at the intersection of this SFK by K and N plus delta lines, and those would give us steady state points. So you'll get multiple steady states. Now notice that if we did not introduce this range where average product was rising, then this curve would have just fallen because of diminishing marginal returns. F prime K would have been negative and this would have just fallen throughout. But because you have a range where average product of capital is rising, that's why you get these multiple steady states. Otherwise, you would have had just this one. These ranges would not have been there. You would have just got a single steady state. All right, now let's explain this. Let's see what's happening here. So as what I explained briefly in the beginning, that when you have multiple steady states, you have a case of trap when the middle one is unstable and the lower and the higher ones are stable. So, so if that's the case, then all the countries that are in this range, those are trying to accumulate greater and greater levels of capital labor ratios. They will be able to cross this and reach here only if their K is greater than K star middle. Till the point their capital labor ratios are below that, even if they are increasing their accumulation of capital labor ratios, they will still not be, all in vain, they will still not be able to reach to a higher level. So it's very difficult for a country which is in this range between K star low and K star middle to be able to reach K star high. The system is taking them towards K star low. And because the system is taking them towards K star low, the forces are against them. So these countries, this set of countries are always forced towards K star low, and they end up with what we call as the poverty trap.
Ma'am, how can we show that in this area, like if they increase capital, they'll go back to K star low?
Yeah, so you're basically asking me about the arrows of motion. So how do we know that this is the arrow of motion here? Yeah, so you can just look at K dot by K. What's happening to the transition? So if you're not at the steady state, then you work out K dot by K in this range. And it so turns out that when you work out this K dot by K, this will be negative for this range. And it will be positive for this and this range. So this is basically the growth rate of capital stock, K dot by K. So you're saying that the capital growth rate will be negative here in case between K star low and K star middle. So let's work out first the expression for GK. And then we'll see that this GK will involve the average product of capital. And therefore, not the average product, but you'll be able to see that for K less than K star low, this GK is positive, and for K greater than K star low, GK is negative. So that's why, and of course, till K star middle. So if you work out those expressions, here it's given to you in the textbook itself. You can work those out for yourself and check. But you won't be able to work them out accurately because the functional forms, let me just check if these are functional forms are given or not.
Ma'am, we could derive this result even from what we have solved and got in the previous question, right? We know that if initially it's greater than the lower steady state, then the capital will decrease and it will go back to the previous.
Yeah, but so you notice that, as I said, what will ensure the existence of a steady state and what will ensure the stability of the steady state. So basically, I mean, I don't want to go into that entire literature, but it says that whenever you have a steady state around which, now this is a shortcut. I mean, don't, there is a huge literature beyond which discusses this possibility of existence of unique and multiple steady states, but I'm just giving you the shortest way to understand this, how you will know that this is stable or not. The steady state around which the production function is concave, it's going to be stable. And the steady state around which the production function is convex, it will be unstable. So let me just check whether we will be able to use this or not. So the idea is that, let me share the whiteboard. So you do have KT plus 1 and then KT functions, which all depend upon, now I'm working in discrete time, you know, because that's the only way I can explain this to you. So we are saying that if you have this sort of KT plus 1 function, which is equal to some equation, transition, steady state equation, transition equation, you have state transition. So this is equal to some function of KT. So this is what we call as the state transition equation. And if this is concave, then what you're basically saying is that if this is K star, you start off with KT here, right? Now, if you map this here, KT plus 1, you will reach here in the next period. Let me say this is period 0. So in period 1, you will reach here, which is K1. Now in the next period, this is your initial value of capital. So this is a 45-degree line. So in the next period, if you just map it on the 45-degree line, this is where you are, K1, right? Now in period 2, your K2 will be here, right? So basically what's happening is you're moving from here, and now K2, if you'll map on the 45-degree line, this is here. So you're moving towards the steady state. Why? Because this is concave. Had it been convex, this is again the 45-degree line. Let me write now convex function. This is KT plus 1 is equal to a function of KT. Again, this is the state transition equation. And here on the vertical axis, you have KT plus 1, and the horizontal axis, you have KT. I have to work in the discrete time to be able to tell you why this will be unstable, but just draw the inference from here. So if this is K0, K1 will be here, right? This is K1. But now in the next period, this K1 has to be mapped on 45-degree line. So your K1 is here. So although this is your steady state K star, you're moving away from it. You slowly move away from it. If this function is convex, had it been concave, you would get a stable steady state. So these are all graphical ways of understanding how you would get a stable or an unstable steady state. But mathematically also you can work these out, but because those have not been discussed explicitly, so I'm just refraining from doing those here as well. But you can work these out to be why they are stable and why they are unstable. Let me go back to the textbook. So in the discrete time, I've just told you why, you can work out by just looking at the curvature of your state transition equation, whether it's going to give you a stable or an unstable steady state. Notice that there are many other possibilities. Let me go back for a while again. So here, this was one. The other part is if you have this sort of a thing. This, and then this, and then this. Suppose that's the case. So what do you think? So you have one K star, then 2, another K star. And suppose if it were to cut here, then another K star. This is low. Let me say this is middle. Let me say this is high. Now what will happen? So around this steady state, if you had this line cutting from left to right, from up to, this way, if this curvature is going this way, then you will have a stable steady state. At this stage here, it's going from here to here. And here also it's going from here. So I don't know how to put it across to you, but if you look at the curvature to the left here, this is concave. If you look at the curvature to the left of this K star, this is convex. And if you look at the curvature to the left of K star high, this is again concave. So these curvatures are basically, so again, if here you would look at the movement of capital, it will be towards this line. And here it will be away from this line because it's convex here.
Ma'am, may I can give a logic behind this? Why it is like going, you are moving towards stable. So ma'am, in the very first part below K star low, saving is higher than the depreciation. So ma'am, in the next period, since saving is high, so
you're not audible.
Excuse me, ma'am, please can
Yeah.
you go over this again?
Yeah. So I was saying that as I just said, if you just look at the discrete time diagram, if you were to just plot it on the 45-degree, if I were to plot a 45-degree line and plot the state transition equation, it depends upon FKT, the production function, the curvature of that. And if that is basically concave to the left of, so he's rightly saying that here, in this case, SFK will be greater than N plus delta. So here you will be able to accumulate capital. Why? Because N plus delta, if you were not to accumulate capital, suppose capital labor ratio stays here at 1. If you were not to accumulate K or L, then in that case, capital and labor is growing at the rate N. So if the denominator is increasing, let me say this is 0, 0, and 0. So if labor force is growing at a rate N and you reach L1 and your capital stock is this again, K naught, you're not accumulating capital, then your K by L will decrease at N. And if capital is also depreciating at a rate delta, and this is K, let's say K1, where K1 is 1 minus delta K0, suppose that's the case. If capital is also depreciating at delta rate and labor force is growing, if you were not to accumulate more capital, then the net rate of decline of capital labor ratio would be N plus delta. This is the net rate of depreciation of capital, so to say. So you're saying that in order to account for increasing labor force and to also account for depreciating capital stock, you need to accumulate, you must have savings which are at least SFK equal to N plus delta. Then in that case, K by L ratio will stay the same and you are in the steady state. But if SFK is greater than N plus delta, then you are basically accumulating capital. Your K by L ratio is not the same, it is rising basically. If SFK, if savings were just enough to account for depreciation of capital and account for increase in the labor force, then your K by L ratio would stay constant. K will remain the same. But if this is greater, then you will have a K which is increasing over time. So in this range where you have, so in this range, let me draw another diagram. So now this is in terms of SFK. And here you have N plus delta. Right? So here in this range, you have SFK till here in this range, which is greater than N plus delta. This line is denoting N plus delta. This curve is SFK curve, right? So that's why you will have accumulation, you will have K which is increasing. When at this point, A, let's say at A, SFK is equal to N plus delta. So your K will remain constant. And beyond A, SFK is less than N plus delta. So K will decrease. So here growth rate of capital, GK will be positive and here GK will be negative. Not, not to say negative, but yeah. So GK will be negative, right, absolutely. So basically we are saying that in this framework here, K will rise and here K will fall. Yeah, there are different ways of doing this. This is a comment. Okay. So, all right. So I hope I have been able to convince you regarding the stability of why steady states and why they can be unstable. So graphically also, intuitively also, and using some discrete time version also, I've told you why some steady states are stable and why the others are unstable. So using the same logic, if you apply on this model, you will be able to derive that the middle one is unstable while the left one and the right one is unstable. So basically what's happening behind this is this part. In this model, this is what's happening. And that is why you will get the middle one as the unstable steady state.
Ma'am, in the previous diagram, if capital is less than K star, at a time, ma'am, growth of capital will be positive, but it will declining. Like it will go 5 to 4, 4 to 3. But
Yeah,
it
we are
will
not. Yeah, we'll see that. So there is another way of deriving those things. So now you're talking about what will happen to the growth rate of capital. What will be the curvature of that? So that I suppose will look like this. It will look like, just a second. So I don't want to draw too many diagrams, but this is what the growth rate, G, K, T, if you want. This is what it looks like around the K star. So this is basically 0 and around at K star. So we know at K star, the growth rate of capital stock is 0, right? This is what we know because K star is something that capital stock is not growing. So the growth rate is 0. So to the right of K star, growth rate will be negative. And to the left of K star, growth rate will be positive because at K star, we know GK is 0.
Ma'am, in this part, the question says use the factor income approach. So what's the factor income approach here?
Yeah, so we have basically said that there are some, on the production side, we have said that there are diminishing marginal returns to K and there are increasing marginal returns to K. And then again, there are diminishing marginal returns to K. So basically, the returns to factors of production is changing, which is why it's giving rising to a different sort of a production function, and which is why you're getting a trap. So you can get liquidity, you can get poverty traps. Many people in the literature have established the existence of poverty traps using different approaches. So this approach that is given here is basically utilizing the fact that there can be a range where there can be increasing returns to factors of production, or there can be decreasing returns to factors of production, and using that approach we have established the poverty trap. There are other models in the literature that establish poverty trap, but not by changing this assumption, by changing the assumption on the savings. So that approach we have not discussed in this course till now.
Okay, thank you.
Yeah. All right. More or less, I'm done. If you have any doubts, then just let me know.
Ma'am?
Yeah.
Ma'am, what are your timings of your office hours?
So if you want to particularly meet me in Delhi school, then tell me accordingly, or you can just drop me an email and I'll tell you when I'll be available in DSC.
Okay, ma'am.
Right. Otherwise, you can send me your queries on email also.
Okay, ma'am.
Ma'am, I want to ask one doubt. Ma'am, the speed of conversion, ma'am, beta is equal to the growth of capital upon the log of that capital. Right. So, ma'am, why we have taken log in that? We can also find that out by taking log of K. Because we are just wanted to know when capital increases, how the growth increases, like at what rate. So why?
Your voice is breaking a little, but from what I've understood, you're talking about beta.
Yeah. Ma'am, my doubt is why we have taken log in that. We can also take just K.
No, because logs help you give growth rates. So, okay, acha, you're asking a very basic thing actually. Yeah. So you're saying that when we say beta is equal to del K dot by K upon del log K, that's what you're asking.
Yes, ma'am, yes.
Why have we have taken logs?
Yeah, ma'am, we can also derive the same results by taking K, because the motive is just to find out how's the growth, that is K dot by K, is changing, or like what's the behavior of this when K is changing. So why we have taken log of?
Because this is by definition, and of course log is a positive monotonic transformation, so you're right that qualitatively you will get the same results because log is a positive monotonic transformation. But usually when we calculate the growth rates, then if you remember in econometrics also, we say that if you have log of y is equal to alpha plus beta log x plus ui. What is the interpretation of this beta?
Ma'am, it's just when there is change in like 1% change in the x, what's like how much percentage y changes?
Correct. That's right. And it is also interpreted as the growth rate. It is also interpreted as the growth rate. So if you have so how do I put it across? So so if you take logs, it helps you give growth rates. Now by mathematically, so beta basically gives you how change in percentage change in y by 1% change in x. So it in some sense gives you elasticities, but if you look at log of del k dot by k by del. So if I were to take k dot by k here and alpha plus beta log k, I don't know. I think it's by definition. And so qualitatively, the results would be the same because log is just a positive monotonic transformation of any variable. But by definition, this beta is defined like this. Okay. The entire literature, we use it this way only.
Ma'am?
Yes.
Ma'am, I missed the part where you were explaining why the case to the left of steady rate, that is K star, is to the right of K star is inefficient.
Okay. Okay. Yeah. So so here I was saying that to the right of K star, you have to, so basically to the right of Kg star, you have cases of dynamic inefficiency because at Kg star, your consumption is maximum. Consumption star is maximum. To the right of K star, you have just over accumulated your capital. And to be able to achieve the maximum consumption here, what you just need to do is just not accumulate capital, which means that you can enjoy higher consumption levels today, not accumulate too much capital for tomorrow. And at the same time, in future, in the steady state, you will be able to enjoy Kg star as well. So by accumulating less, you will be able to enjoy consumption today, more consumption today, as well as in the future. So you have not lost anything. So you're basically sitting at a point of inefficiency. You could be better off today as well as tomorrow by just accumulating less capital. But to the left of K star, if you were to reach Cg star, which is maximum levels of consumption in the steady state in future, you will have to sacrifice current consumption and be able to accumulate more capital so that you are able to reach Kg star, which will give you Cg star in the future. So at present, you're sacrificing some consumption to be able to achieve higher steady state levels of consumption. So which is that you're not better off in every sense. So this is a point of efficiency, dynamic efficiency. To the right, you can be better off without being worse off either today as well as in future in the steady state. So that's why points to the right of Kg star are points of dynamic inefficiency.
Yes, ma'am. Okay, thank you.
Okay. All right, then I'll close the session for today. And in case you have doubts, you can mail. You can send. Yeah.
Ma'am, stochastic Solow model is a part of syllabus for midterm or not?